Now let's see how this principle is applied with a problem example. So we have the roller coaster starting at some known height and from rest. So this tells us that the initial velocity is then 0, and it follows the track. Eventually will reach the highest point of a circular loop, and the question is, how fast is the roller coaster moving at position B, at the highest point on the circular track? So let's first analyze what objects are part of the system. The problem is clearly related to the variations in height of the roller coaster, which means gravitational potential energy here will be important. It's continuously changing. So the system will consist on the roller coaster and the planet Earth. Because remember, without the planet Earth, there would not be gravitational potential energy. The other important thing that is mentioned is that the track is frictionless. This is important because if there was friction would do work on the car, and friction is not a conservative force. So it won't convert kinetic energy into any type of potential energy. So friction will produce heat at the surface of the car and the surface of the track, and that heat will escape from the system. So kinetic energy is converted into heat that then escapes into the atmosphere. It dissipates into the atmosphere. So friction force is not a conservative force. That's why it's important that we assume for the moment that there is no friction. So the track is frictionless. Of course, this is an idealized case, but we will learn in future sessions how to remove those idealizations. So let's start by creating a list of initial known quantities. So initial quantities that we know are the height of the car. We know the car starts from rest, so the initial velocity should be 0. On the other hand, when the car is at position B, which we will choose as our final position, at that point we can see that the height of the car will be 5 plus 16. So we get 21 meters as the initial height. Note that here we have taken as the reference zero level the level of the ground. We could have chosen any other reference height, let's say the initial position of the car, and that would have been fine as well, but then we would need to calculate the position B as measured from position A, which would give us some additional calculations. So taking the ground as a reference zero level works fine. Now, the velocity at position B is unknown, and actually that's the quantity that we are trying to calculate. So, since mechanical energy is conserved here because of the frictionless track, we can write the conservation of mechanical energy equation. So we have kinetic energy at the final time, gravitational potential energy at the final time, elastic potential energy at the final time. And then we have the equivalent terms on the other side for the initial time. Now, some of these quantities are zero or not relevant in this problem. To start, we can see that since there are no springs in this system, we can simply discard the elastic potential energies. On the other hand, we know that the initial velocity of the system was zero, which means the kinetic energy will be zero at the initial time. And then the equation will simplify. And we can write the equation explicitly in terms of other quantities. Now here we realize that the mass of the car appears in each term of the equation. So we can divide. By the mass all parts of the equation, and the mass will cancel. And we get from here we can isolate the quantity that we need, which is the final velocity. And I will give you the expression that you should obtain if you do the algebra carefully. And we are ready to substitute values in this equation. Which after rounding we get a speed of 13 meters per second. So that will be the speed of the car at point B.